Hello, welcome to my channel. My name is Maxim Omanyamanga, and today we shall go through the amortized analysis. What is amortized analysis? In amortized analysis, the time required to perform a sequence of operation is averaged over all the operations performed. Again, in amortized analysis, there is no involvement of probability. The average performance on sequence operations, even some operations, is expensive. It guarantees average performance for each operation among the sequence in worst case. Therefore, amortized analysis is not just an analysis tool, it is also a way of thinking about designing algorithms. So we shall look at different examples or styles of amortized analysis. To start with, we look at the aggregate method of amortized analysis, which determine an upper bound Tn, T of n, on the total sequence of n operations. The cost of each will be n Tn divided by n. And in the accounting method, we shall see the average, we shall see that we overcharge some operations early and use them to as prepared charge for later operations. So for potential method, we maintain credit as potential energy associated with a structure as a whole. Let's look into details of what this analysis do. Aggregate analysis or aggregate method. This one shows that for all n, a sequence of n operations take the worst case time Tn in total. In worst case, the average cost or amortized cost per operation is T of n divided by n operations. The amortized cost applies to each operation even when there are several types of operations in the sequence. Let's look at the different operations here. We look at the push, pull, and multi-pop. And in this case, we're saying that the push is when you're adding things onto the stack. So there's a stack example. Then the pop is when you're popping something out of the stack, and multi-pop is when you're popping out more than one item from the stack. So we see that the worst case time for each operation in aggregate analysis is big O1. For push, also big O1 for pop, and big N, big O(n) for multi pop. The S is the stack, and then the K is the number of multi pops you want to pop at that time. And then the X here is the items being added on the stack. The amortized cost is big O1 of 1 per operation. Aggregate analysis stack example, we observe the following things: sequence of n pushes, n push, n pop, and n multi-pop operations. And in that case, the worst case for multi-pop is big O of n. And then we know that we have n operations, therefore the worst case cost of sequence is big O of n. We observe that also some of the observation is that each object can be popped once per time that it's pushed. So you can't pop, in other words, what is not pushed. So if you push in n items, you can only pop only n items, not more than n. So we have less than equal n pushes, then you have the greater or equal n pops, including the multi-pop. So the average cost or total cost is big O n again. The average overall operation is greater for each per operation. You have big O n divided by n. So per operation you have big O1 as the time or the cost time for that for any operation, either pop, push, and multiple. You notice that there is no probability involved in amortized analysis in general. Method number 2 is a counting method. In this case, you look at a charge. We charge ith operation, a fictitious amortized cost, C sub I cap, where $1 pays for 1 unit of work, or in other words, time. So we assign different charges at the amortized cost to different operations. Some are charged more than actual costs, and therefore the some are charged less. This fee is consumed to perform the operation. Any amount not immediately consumed is stored in the bank for use by subsequent operations. The bank balance, also called as credit, must not go negative. So the bank balance always have to be positive for this kind of operation. Then we see we must also ensure that for all n, the sum of the actual cost from I equals to n to m should be less or equal to the summation of the amortized cost from I equals to n equals to 1 to n. Thus, the total amortized cost provides the upper bound of the total true cost, or actual cost. Now let's look at the stack example for the accounting method. We have again the 3 operations: push, pop, multi, pop, stack. So we have our stack S, and you're having X items being added, and then you have a stock which is being popped, each item one by one, and multi-pop. S is the stack, and the K is the number of items to be multi-popped. So in this case, when you push in an item, we pay $1 and pay an extra $1 for future use. That will be the credit that will be storing in their bank. Therefore, the actual cost is 1, but the amortized cost is $2, if you remember our example there, the explanation back there. So $1 for the push and an extra $1 for future use, and which is our credit. So we have 2. The cost is 2. Now you notice that after you've pushed enough items into the stack, therefore the next thing is popping. So if you want to pop one item, the actual cost for popping is 1, and you will not be charged anything else because that particular item was already prepaid the amount of money to be used to pop. So therefore the amortized cost will be 0. The same for multi-pop. Notice that each time you pop an item, you charge it twice the amount. So however much the multi-pop will be as well, those particular costs were paid up front. So the actual cost is the minimum of the absolute value of the stack plus the proposed multi-pop, and the cost will be 0 because it was paid from the credit that is in the bank. So let's look again into details, into the accounting method, stack example. So when pushing an object, we pay $2 for that. So the first $1 pays for the push, The second dollar is a prepayment for it being popped by for it being popped by either pop or multi-pop. Since each object has $1, which is credit, the credit can never be or can never go negative. Therefore, the total amortized cost is big O n of n, and is an upper bound of the total actual cost. Just a simple example again. Take an example of a restaurant where you're already arranging a stack of plates. So when you push in a plate into the stack, you pay $1 for the push, and you put $1 on top of that plate that you've pushed. So that means for a single operation, we spend $2. And when you're popping that particular plate or you're removing that plate from the stack, the dollar that is right on top of that item that's being popped is the price for that. So the actual price is 1, but the amortized cost was already sorted out during the push operation. Another method is potential method. The idea here is view the bank account as a potential energy. In other words, as in physics, the dynamic set. And in this potential method, we are looking at a couple of things. Start with an initial data structure, which is D sub O. The operation I, which is a transformation from di minus 1 to di. The cost of operation of the ith operation is C sub I. Then we define the potential function as phi d1, which is equal to the real number, such that the phi of the initial data structure equals to 0, and the phi of the preceding or the upcoming operation should be greater or equal to 0 for all I operations. And the amortized cost, C sub I cap, with respect to the phi, is defined as the amortized cost equals to the actual cost plus the difference between the data structure of the particular operation minus the initial data structure. Like the accounting method, we see that the potential method resemble, but think of the credit as a potential stored with the entire data structure. So notice that the credits in the accounting method, the credit was kept for each item or for each item on the stack. But for potential method, the credit in this sense is stored as an entire structure. It's part of the structure. The systems is stored as a structure as compared to just items per stack. Per stack. Accounting method stores credit with specific object, while potential method stores potential in the data structure as a whole. And it can release the potential to pay for future operations. And this is mostly flexible for amortized analysis method. So we already seen this formula, and therefore the computation at this point is we call it the potential difference between the structure at that operation minus the original or the initial structure. So if the difference is greater than 0, then that means that the amortized cost is greater than actual cost, and therefore the operation I stores work in the data structure for later use, so that additional credit will be stored for later work in the structure. And if the difference here is less than 0, then that means that the amortized cost is less than the actual cost, and the data structure delivers up the stored work or the stored credit to help pay the operation at I. And in simple calculations, you can deduce this, or you can denote this difference or subtraction as S plus 1 minus S, which is, if you expand this, the S and the S will cancel each other and then will remain with 1. So let's look at the equation again. The total amortized cost for n operations is the summation of the amortized cost from I equals to 1 to n plus the sum of this computation from n I plus 1 I equals to 1 to n of the actual cost plus the difference plus the difference between the operation cost and the data, the initial data, the operation data minus the initial data. So summing both sides telescopically, we boil down into this final equation. Since the dn is greater than or equal to 0, and the d0 or d naught equals to 0, therefore this part will die off, and the the summation of the actual cost. As we continue with the stack example, we see that the di is the number of items in the stack, and the d naught equals to 0. That's the first, so when the stack is empty. So let's plug into this. Into the operations. So if you look at the push operation, we have the equation Ci, the amortized cost equals to the actual cost plus the difference. So pushing one item will cost you the actual cost to be 1, and therefore remember the equation how we summarize this into this. So you'll be able to be stack plus, we're adding one item, so the cost is also 1 minus stack. So this plus this will cancel. Therefore, the amortized cost for pushing one item in the potential method is 2. The amortized cost is 2, or $2 if you want to look at it that way. So when you're popping, again, you're popping one. If you want to pop one item, so far you have one item in stack, and therefore our formula will be what says S minus 1. Since you don't know the cost for popping one item is, you're going to subtract that. So the S and S will also cancel out, and shall remain with the minus 1. So 1 minus 1 equals to 0. So the amortized cost is 0. And you notice that the price was paid earlier. That is going to be that is used. So we can't, the amortized cost doesn't need to be consumed. We store that as credit. Then when it comes to multi-pop, so this is a number of items that you need to multi-pop plus the stack minus the multi-pop that is being executed minus the S. Again, you will notice that the S and the S will cancel out, and it will be K minus K, which is a 0. So again, multi-pop, the amortized cost is 0. This is exactly the same thing as I've explained previously in a nice table format. You got to see what's happening. So 1 plus 1, 2 minus 1, 1 minus 1 equals 0. The K and the minus K will also be 0. The amortized cost. The actual cost is negative 1. So the amortized cost is an upper bound of the actual cost, which is big O n. Finally, the last amortized method is the dynamic table. It's a nice use of amortized analysis. You do the table insertion and table deletion. The scenarios in this dynamic table is that a table may be a hash table. We do not know how large the table will be in advance. May expand with insertion, may contract with deletion. detailed implementation, sorry, is not important. So again, we see the goal here is big O1, amortized costs for each operation. So is unused space always, it should be less or equal to the constant fraction of the allocated space. So here you're looking at the load factor alpha, which is equals to the number of items in the stack plus this divided by the size of the stack, where the number is the number of items stored and the size is the allocated size. Okay. If size equals to 0 and the number equals to 0, then they call alpha equals to 1. So a hint here is that we never allow alpha to be greater than 1. So we're supposed to keep alpha greater than a constant fraction, which equals to the goal 2. Let's look into details what's happening here. So this is an table expansion. Consider only insertion. When the table becomes full, it doubles its size and reinsert all the existing items. What happens again? It guarantees that the alpha will be greater or equal than a half. Each time we actually insert an item into the table, it's an elementary insertion. Let's look at this pseudocode. We see that the table insert, the table, this the item we're inserting. If the size equals to 0, then allocate the table with a slot, with one slot. So table size will be 1. If the number of items in the table equals the size of the table, then create a new table which is 2 times the size of the table and slot it. So we double the size, we double the facility of the storage by 2 to accommodate the new item. Therefore, insert all the items in the table T into the new table that you've created, the double table. Then free the table T, the old one. Then therefore, the table T will be able to be given the new, will be equal to the new table. The table size equals to 2 times T. Then insert into the table. Then the number of items equals to the number of items in the table plus 1. So this keeps running over and over and over again. Notice that the initial number of table equals the size table, which is equals to 0. So as you keep inserting, it will run through the code, and each time if the number of items in the table equals to the size of the table will double the capacity it has. If it has 1, it will double that to make 2. If it has 2 spaces and the number of items is equal to the number of items 2, the storage will double that and you have 4. If you have 4 and it gets full, you double that and you get 8. And that keeps going on and on and on. So let's look at this table. Assume we have an example of a puppy shop. So somebody wants to buy puppies and he wants to stock his shop with puppies. And so the first time, the facility is empty, has nothing, it is 0, and therefore the cost is 0. So when he buys 1 puppy, that will be operation 1. Therefore, he has to double the size that he had there, so he has to get at least 1 space, and the cost will be 1. Then if he buys another puppy at operation 2, now he has 1 puppy already in the stock, and he's adding another one, and the facility has only the size 1, so it needs to double this. So the cost will be 2 to create the new house, and therefore it will transfer the old puppy into the new facility and add in the new, so the cost will be 2. Then he procures another dog, number 3. He brings, but he finds that the storage is still small, so he has to double the size of the storage to 4, and therefore he transfers the old dogs from the old facility to the new facility, and so the cost is 2 plus the dog was be 3. So he gets the 4th dog, then he checks he still has the storage. The storage is still enough for 4, so there's no need to expand. So therefore, he just adds that new dog into the stack, so the cost will be 1. So if he gets the 5th dog, the storage is small, so it needs to double the storage, so the storage will be 8. So the operation is transfer the dogs from the old facility to the new facility, and plus the new dog, the operation will be 5. Add the 6th dog, the facility still has space, so there's no cost. The cost will be the same cost and therefore just be adding that dog into the empty facility within what he has already. The 7th dog, again, will find the facility has space, so the cost still remains, the size still remains 8, and the cost of inserting that dog will be 1. He gets the 8th dog. The facility still has 1 more slot, so it can still accommodate, and the cost is 1. When he gets the 9th dog, facility is small, he needs to double the facility. Now it's from 8 to 16, and therefore the operations or the cost that he needs to use for transfer the dogs from 8 dogs from the old facility plus the new dog, and the cost will be 9. So basically that's how the dynamic table works. Thank you very much. I hope you have enjoyed amortized cost.